Hello everyone, my name is Mohit and I'm thrilled to present my master's thesis. The thesis is titled as Low Parameter Mamba, a challenger to transformer based models. Today I'll walk you through my research comparing the innovative Mamba architecture with the transformer architecture based models for text classification with a special focus on hyperpartition news. So let's dive in. This is Mohit. I'm a senior data scientist at a fintech organization called Tide in UK. So moving ahead. So today we will cover these six chapters, starting with introduction. Then we outline the aims and objectives of the research, followed by a glimpse or a gist of literature review, and then we cover the methodology or the techniques used in this research. And finally, we discuss our analysis, the results, and then we conclude with answering the three questions with which we started the research. So let's dive in. Introduction. Natural language processing or NLP is at heart of how machines understand and process human language, powering applications like translation, sentiment analysis, and more. One pressing challenge in NLP is detecting hyperpartition news. Basically, they are articles that show extreme political bias, often distorting facts in such a way that they prefer or they tend to prefer some specific parties or group of people. So, in today's digital age, misinformation spreads at a rapid rate, and moreover, with increasing usage of tools like ChatGPT and other similar large language models, and there have been a surge in fake news, and this makes it critical to develop efficient NLP techniques that can identify bias in real time, especially for lengthy news that require most processing. So, transformers versus emerging alternatives. Transformer based models like BERT and Roberta have dominated NLP thanks to their powerful self attention mechanism, which capture contextual relationship in text. However, they come with a significant drawback. Their quadratic complexity makes them computationally expensive, especially for long sequences like news articles that often exceed 512 tokens. This inefficiency limits their use in real time applications. So, we have a new contender in the arena, Mamba, a state space model taking pride in its linear time complexity, specifically designed for efficiency. Further, the research focus is only on transformer and Mamba models, which are less than 1 billion parameters, and specifically in the arena of text classification. Moving ahead, now we list the aims and objectives of the research. The main aim of my research is to identify the most cost effective model for text classification by comparing sub-billion transformer models such as XLNet, BERT, Roberta, DBERTA with Mamba variants, specifically Mamba 130 million and Mamba 370 million model. The focus is on hyperpartition news detection, a critical task for combating misinformation. To achieve this, I set three objectives. First, I evaluate model performance across five benchmark datasets using standard metrics like micro F1 score, Matthew correlation coefficient, and along with it, there are others like precision recall, quite a few, including confusion matrix and ROC curves. Secondly, I analyze how parameter count affects performance in smaller models. And thirdly, we assess Mamba's scalability and efficiency, looking at training time and floating point operations and the power consumed, etc. These objectives are shown here focus on practical solutions to for resource constrained environments. Now let's review the background that shaped this research. Moving ahead with the literature review, the field of NLP has transformed by the introduction of transformers in 2017 by Vaswani and colleagues. Their self-attention mechanism allows model to capture bidirectional context, revolutionizing tasks like text classification. Key transformer models include BERT, which set benchmarks with its bidirectional pre-training, Roberta, an optimized BERT with trained on larger datasets, and then Debata, which uses disentangled attention to surpass human performance, and XLNet employs permutation-based training to handle long context effectively. So, despite people using transformers, there has been a known issue with the architecture itself. So, transformer models suffer from quadratic complexity, making them inefficient for long sequence tasks. Despite this inefficiency, transformers are widely used in many fields of NLP, such as text classification, sentiment analysis, entity recognition, and etc. So, however, this limitation um, helps to push the field of research forward, prompting researchers to explore alternatives. Let's discuss such an alternative. The rise of state space models in Mamba. State space models, or SSMs, have emerged as a promising solution, offering linear time complexity that's ideal for long sequences. Among them, Mamba stands out. Mamba uses selective state space layer, or X6 layer, that dynamically focuses on relevant parts of the input, reducing the computational load while maintaining robust performance. It boasts 5 times the throughput of transformers and a way low memory footprint, comparable to advanced techniques like flash attention. Despite the research and the advent of language models, there is a research gap. Few studies have compared Mamba and transformers on text classification, especially for complex tasks like hyperpartition news detection. So, my work fills this gap by systematically evaluating these models, and let's see how I did this. To compare Mamba and transformer models, let's start with methodology. To compare Mamba and transformers, I used 5 benchmark datasets, starting with hyperpartition, AG News, 20 news groups, SST, and IMDb datasets. So, despite the known fact that transformer models and perform generally well with little pre-processing, the datasets like hyperpartition and 20 news groups demands an extra pre-processing steps due to their nature of text involving HTML tags, URLs, and non-ASCII characters. So it's good to pre-process uh, so that we achieve optimal results. And we also explore different class imbalance techniques in the research methodology, finally landing on using weights to for each specific label, inversely proportional to its volume, so that um, low density labels are learned effectively. So we have our models or contenders, starting with XLNet, BERT, Roberta, Debata, Mamba 130 million parameters, and Mamba 370 million parameter model. And we use Hugging Face API to train each of these models against each of the datasets here. So, and then we finally evaluate the models on macro F1, MCC, um, ROC, precision, recall, flops, training time, and throughput, etc., covering both performance and efficiency metrics. Moving ahead with results and discussions, the results were striking. Across five datasets, Mamba achieves the highest mean F1 score of 90.6% with a tight confidence interval. In hyperpartition news detection, Mamba scores an impressive 93.6% F1 score, outperforming Dibata. It also matches or exceeds transformer models on other datasets like AG News and 20 News. The key strength of Mamba lies in its efficacy in handling long sequence tasks due to its linear time complexity. To visualize the trade-offs between quality and cost, we plot training time against mean F1 score averaged across all benchmark datasets, with bubble size representing the number of parameters. In the category of small and base variants, the Dibata V3 base demonstrates superior performance, outperforming not only other transformer-based models such as XLNet and Roberta base, but also Mamba 130 million model. The Mamba 130 million model performs comparably to its nearest parameterized transformer models like XLNet and Roberta base, and even Roberta large, indicating its efficacy at smaller scales as well. In contrast, if you see on the top right, within the large group, Mamba 370 million achieves the highest performance despite having lower parameters than Dibata V3 large. This suggests a trade-off between peak performance and training cost. Notably, within the same transformer family, Bates and large variants tend to exhibit only marginal differences in F1 scores. For instance, Roberta Base and Roberta Large have similar performance in terms of F1 score, as well as with the case with the Roberta V3, the base variant performing similarly to the large variant with marginal difference. Coming to the efficiency comparison, the table on the right side shows various dimensions uh, through which we can compare the efficiency of these models. Mamba 370 million model achieves the highest accuracy at a lower computational cost, as much as one sixth of the computational cost of Dibata V3 large, which is the closest model in terms of number of parameters to Mamba. And in terms of memory usage, if you see at the total number of floating point operations, Mamba models take significantly less number of computational operations for training. Uh, Whereas if you see the transformer models, they are considerably large. And more specifically, if you look at the Mamba 370 and the Beta or BERT with similar parameters in the range of 300, we see there is a significant increase in the total number of computational operations taken by transformer models in comparison to Mamba, suggesting Mamba's selective mechanism reduces memory footprint similar to flash attention in transformers. Out of the large variants, Mamba shines brightest using less computational operations. However, Mamba suffers from high training times and low throughput despite using low computational operations. So, suggesting there is need for efficient implementations and optimizations. Complementary radar plots in this slide normalize seven key metrics into a unit scale, enabling comparative analysis across two groups of models. On the left hand side, we have base group, and on the right hand side, we have the large group. In the base group, on the left hand side, Dibata V3 base performs or Dibata demonstrates the most balanced of performance profile, showing strong results across most metrics. It is followed by XLNet base and Roberta base, while Mamba 130 million lags behind, indicating a room for improvement. And uh, and uh, yeah, in the arena of base models, Mamba doesn't shine. to be clear. And in the large group model on the right hand side, Mamba stands out with dominant scores both in F1 and MCC, though it underperforms in evaluation throughput and exhibits prolonged training time. So this further suggests an area of future optimization. Despite being Mamba best in terms of performance scores, it suffers severely in efficiency scores like throughput and total training time, suggesting further research to include better implementations or optimizations to really realize the theoretical results. Alongside, Debutta V3 Large and Roberta Large are the in the large arena, the top performing models in this category. So moving ahead to conclusions and future recommendations, we started with three research questions at the beginning of our research, and here we finally get to answer the very questions with which we started the research. The first research question: how does Mamba and transformers compare in terms of performance and scale, specifically on hyper partition dataset? So we have seen from the results that Mamba 370 million variant outperforms transformer models in text classification. And the research question two: what are the advantages and disadvantages of Mamba with respect to accuracy and efficiency? Mamba supports superior accuracy and computational efficiency, but lags in throughput and training speed, necessitating efficient implementations or optimizations. Third research question: is there a correlation between parameter count and performance? Mamba models, the model parameters and F1 score show a moderate correlation, indicating that while while in general larger parameter model performs well, but it's not necessarily the case because architecture innovations like Mamba, for example, which uses selective state space mechanism, can outperform larger transformers, as we have seen in this research. Future directions: the most important future direction and the immediate direction of the research should be in optimizing Mamba's training at kernel level so that we get better uh, training times, and then explore the Mamba architecture on other NLP tasks as well. For example, in this research, we focus majorly on text classification. There are other areas of NLP called named entity recognition, question answering, etc. So they can Mamba models can be studied with how they can perform in comparison to transformers across other fields as well. And the next direction is to develop standardized data sets and metrics for fake news detection or hyperpartition news detection. So we have less number of data sets in this field. And the last direction would be to investigate hybrid Mamba transformer architectures, so that we can get the best of both worlds. So this concludes our presentation. Thank you. Feel free to reach out to this email address if you have any further questions in my research. Thank you.